Good morning. Welcome to the radar system course. Today we discuss here what are the various issues in a ECW radar, or we can say that what are the various requirements at the radar depth. When we talk about the radar, we need to know about that when we receive the echo signal at a receiver, then that receiver should be a noise free, or your system will work. It has a higher signal to noise ratio. But a echo signal received from the target, that echo signal has some limitations on the a threshold level or a level of the signal, as well as there will be an issue related to the bandwidth. Because if you consider that for a CW radar, we say that we consider a CW transmitter section, and then we have the a receiver here. Then we supposed to consider that the same a receiver at this another end. Okay. This in that case, that echo signal, okay, so we can say that there is some particular junction, okay, and that at that junction we are getting the echo signal to the receiver. Some portion of the transmitted signal will reach to the receiver also, and at the receiver we supposed to use a mixer, then a Doppler filter or a Doppler amplifier. Okay, we supposed to use this Doppler filter amplifier, or instead of that we consider that a IF here. Okay, instead of that we supposed to consider the IF, and after that we supposed to consider that Doppler filter. So now here the role of this Doppler filter to identify that what will be the shift in the a frequency signal, means your carrier frequency signal, or we can say that your continuous signal transmitted from the transmitter. So what will be the shift occur? So for that purpose we supposed to say that we have the transmitted frequency signal ft, and there will be a shift, and that shift will be a plus or minus ft. Now that plus or minus ft will indicate whether your target approaching toward the radar or it will be receding the radar. Okay, so now means closer to the radar or away from the radar. Okay, so that plus or minus will indicate there whether it will be a closer or whether it will be away from the that radar. Okay, target will be closer to the radar or away from the radar. Now here, what will be the variation in that FD? Okay, so according to that, we have to design a filter, and that filter will be work at a wide band, because even if there will be a small variation in the frequency change, that is to be observed by the radar. So that's why we supposed to use a wideband filter there. But when we supposed to consider that we need a wideband filter, then there are some limitations regarding the a receiver there. Okay. So what happened here? If there is a large change in the frequency there, then we supposed to use that Doppler frequency or Doppler filter is to be worked in a wide band one. So what will be the expected frequency from the target or echo here, and what will be the spectrum required for this Doppler frequency? Then there will be a requirement for the wideband amplifier Doppler filter. Okay, wideband Doppler amplifier. Okay, that is the requirement there. But when we consider that a wideband Doppler filter, so in that case, because of the introduction of the wideband filter, so then that will increase the noise in the system. Okay, and because of that noise, when we increase, because of that wideband operation of the filter, then it will introduce a noise. If it introduces a noise, then the sensitivity of a receiver will be reduced. So now to work on that, how to improve the sensitivity of the receiver. So in that case, we are supposed to consider that a Doppler filter instead of a wideband one, we are supposed to use a filter in narrowband one, so that a sensitivity of a receiver will be improved. So we consider here what will be the received waveform at this receiver, and what will be the duration of that particular waveform. Okay, whether we are getting the spectrum at the receiver, a finite spectrum or infinite spectrum. Okay, so that is to be understood here. If we have the a filter at this particular end or at a receiver, so if it is a finite one, so in that case, the receiver sensitivity will be increased here. Okay, so means we need to talk about that. What will be the total bandwidth of this receiver, and what will be the receiver sensitivity? If we say that a band is increases, if it will be work at a wide band one, then naturally it will decrease the receiver sensitivity. And if we consider that your operation will be a narrow band, then sensitivity will be increased. Then the issue is about that a your filter. So it will not work for the a wider band. Okay, it will not work for the wide band of a filter. Now to avoid it, okay, to avoid that wide band operation or a narrow band operation, okay, or to improve the sensitivity, so we're supposed to use a Doppler filter. Okay, we're supposed to use a Doppler filter here, and that Doppler filter will detect the wide range of the frequency. So instead of a single IF, it's supposed to use a wide band IF. Okay, if we are using a wide band IF, then your receiver sensitivity will be decreased. Okay, because it will be wide band. So instead of that, if we supposed to use a various IF filter bank, okay, that is IF1, IF2, IF3. Okay, so likewise, if we supposed to use a various filter bank, then that role of wideband operation will be satisfied, and then it will reduce the noise, and then sensitivity of a receiver will be improved. So if you consider that for a variation in the frequency, okay, so what will be the change occur if supposed to be your system have the info, infinite here, okay, band of operation, okay, or we can say that a finite duration. So in that case, if it is the infinite one, and whether it will be a finite duration of system. So likewise. So then what will be your spectrum there? Okay, so we need to talk about that. Instead of work in a infinite duration, we can work in a finite duration with variation in the frequency there. So that there will be the for the finite duration of a filter, then there will be the operation of the receiver will be of a in a wide band one. Okay, so we can consider that a spectrum. Okay, we should consider that a spectrum is to be worked in a finite duration, but overall your receiver will work in a wide band operation, and because of that, the bandwidth of the receiver will be improved, then the sensitivity will be of the receiver will be improved, and so we can consider that the signal to noise ratio, okay, that will be improved here. So we can consider the Doppler shift filter, okay, or that is to work in a narrow band of a operation there. So how it will be a narrow band of operation? We have at a receiver, we supposed to draw a receiver now, that is about a CW radar. This will be the a mixer here. So from the mixer, we supposed to use a IF amplifier, okay, and after that we supposed to consider a various filter bank or a various IF. Okay, so instead of that, we supposed to use a various Doppler filter, filter one, okay, then filter two, then filter three. So likewise, so we can use a n number of a filter, and then that filter, after that, for each and every filter, we supposed to consider that there will be a, okay, we can say that there will be a detector. Okay, so we can say that we have a detector for each. Okay, so we can consider that detector here, and then we can combine the output of all the detector to the indicator. This will be the indicator. So this way we consider. So our aim about your filter is to work Doppler filter amplifier is to work in wideband of your operation. So if we are supposed to use a single filter, then noise will be improved. Yes, noise will be increased. Okay, but sensitivity will not be improved. So to avoid it, we supposed to use a narrowband filters. Okay, we supposed to use a narrowband filter bank here. So they filter one, filter two, filter n here, and then that will be improve the signal to noise ratio, and that will be improve the wideband operation of the a field, wideband operation of your receiver. So means receiver will work in a wideband. Then what will be the response of this particular filter there? Because it is to be work in a finite duration. So every filter is having a finite duration. So if I talk about that a response of the filter, then the response of a filter will be what? So it will be work in a wideband one because we have the IF we defined earlier, and these filters will be overlap each other. Okay, so whatever the response of the filter is to be overlap each other, so that it will work in the what will be the IF bandwidth we define here. Okay, this is about your frequency response of the filter, and this one is about the IF with the Doppler filter amplifier, the Doppler filter here, and this one we supposed to use a bank of a narrowband filters there, and that narrowband filter they are spacing through the whatever the Doppler frequency shift is allowed. So according to that, there will be the spacing in the filter there, and this particular filter bank is to be used to improve the signal to noise ratio. Now this will be work in a what? A wide band, because each filter has a some band of operation there. But if you consider in a total, so you can say that your filter bank, okay, whole filter bank, so it will accept a wide band signal. Okay, it will accept the wide band energy signal. So that even if that single filter will not work in a wide band, it will work only in a narrow band. But overall, your receiver will work in a wide band, And because of that various band of a frequency or various filters we supposed to use, so naturally it will reduce a signal to noise ratio. Okay, so then what will happen there? Your total wideband of operation we supposed to consider that improve the a signal to noise ratio there. And if supposed to be we are not using a separate filter, so then signal to noise ratio will be decreased there. Okay, there will be a reduction. So we can consider that a filter in a such a way that so there will be what will be the if the band will be separate out, so then there will be the wideband operation and signal to noise ratio will be improved. But if you consider that there will be the overlap of the band is occur used here, okay, whatever the overlap in this for a particular filter, okay, so in that case, so it will reduce the a signal to noise. It will not improve the a signal to noise. So that's why we supposed to know that at what particular way to improve the sensitivity of the receiver. If we supposed to use a more number of filters, so then our band of operation of a receiver will be large, which it will work in a wide band operation. And then because of that more number of filters, so then loss will be the less here. But because of that more number of filters we supposed to use, a small variation in the signal that can be catched by the detector or that can be catched by the receiver. So then we can say that there will be the increase in the probability of a false alarm because we are using the large number of filter bands. So we say that a narrow bank of a filters we supposed to be we are using narrow band filters we are using, and that filters are used to detect the whatever the signal. So instead of a single IF and single amplifier, we supposed to use a narrow band, but to you improve the a signal to noise ratio across this at the receiver end. But that will not be improved. Okay, if it will be a overlap filter band. Okay, wideband operation, signal to noise ratio to be improved, and the sensitivity of the receiver is to be improved. So that's why we supposed to use a filter. Okay, we say that there will be the overlapping of the filter. So instead of that, we supposed to consider that a frequency what we are supposed to be expecting. Okay, and what will be the response we are expecting. Generally, we say that this one is about your signal is to be transmitted, and then whether we supposed to find out okay this is about a main signal, whether it will be the f is equal to what we can say that ft is equal to ft plus or minus ft. So whether it will be a plus or minus, okay, whether it will be a plus or minus is about a center frequency. Okay, so now this is about your ft. Okay, so we consider that this one is about ft, is about your center frequency. So in that case, what will be the shift? Whether that shift will be in which direction? Okay, so what will be the positive direction or a negative one? Okay, so means ft plus ft or ft minus ft. Whether there will be a plus sign or a minus sign. Again, that limitations. Okay, to for the given particular spectrum, whether it will be forward or a backward. Again, not satisfied using this particular technique. So means we can because to for ft plus or a minus ft. So we supposed to use a that much bank of filter here for getting the plus or minus ft here. So instead of that, we can consider in which direction your signal will be. Okay, whether that plus fd or a minus fd. To identify that plus or minus fd, we consider that what will be the change in the phase occur? Okay, what will be the change in the signal phase, so that we can easily identify whether your target will be approaching to the radar, okay, or we can say that target will be away from the radar. Okay, so in that case, we consider that a Doppler filter bank, okay, Doppler filter here with a wide band of operation. Instead of that, we supposed to use the narrow band of filter there to improve it. But what will be the expected Doppler frequency through this particular filter can be found here, okay, because we are using a various filters, so we can easily found through this because we are using a various filters there, and we can find through it. But we are not able to determine what will be the a plus or minus sign. Okay, we can say that there will be the variation in the frequency occur, but we supposed to find out that plus or minus sign in which direction. Okay, so that is about the issue. So we can consider another way. Okay, we can say that for the given range, we can find out using the different filters, and we can say that there will be FD plus or FD minus. Okay, so even if there is a clutter signal is there, so then that clutter signal again added. So we supposed to use a clutter rejection filter bank that will remove the whatever the clutter occurs there. So then to measure the direction, okay, means your target is approaching in which the okay target is approaching there. So that target is from the given particular radar. So whether your target is moving toward the radar or moving away from the radar, or if supposed to be, we have the radar here, explaining about a radar, and here is we have a target. Then target is moving from to this direction or that direction. Okay, this is about your target. So in that case, what will be the radial velocity of the target? Okay, in this direction or this direction. Okay, which direction? Okay, so this or that. Okay, so likewise, so we need supposed to find out using the what will be the radial velocity, and then we need to know about that what will be the phase shift occur. Okay, what will be the phase shift occur at a receiver signal at echo. Okay, means echo signal, and then that change in the phase shift that can be defined or that can be identified by the indicator or that can be measured or that can be reflected through the different kind of a motor there. If there is a small, if your target direction is in this direction, okay, target is rotating in that direction. So then whatever the antenna here placed on this radar, that antenna is to be steerable one, and that is to be rotating toward the target direction. Okay, means we say that the target is moving in this direction now. So then antenna placed here, so that is to be moved in that direction. Likewise. So we need to use a motor here. So that motor, okay, this particular motor will allow to rotate, okay, will allow to rotate that antenna in a 360 degree. Okay, so or what will be the requirement? 180 degree. Okay, so either this direction or either this direction. So likewise, that antenna is to be rotated. So we need to find out. So what will be the direction of that target motion, and that direction of the target motion can be find out using the checking what will be the signal received at the receiver. So that's why we supposed to split the received signal. Okay, we're supposed to split the received signal, and then through that we can find out that what will be the change after that. So we consider here this one is about your CW transmitter. Okay, then we have mixer here, mixer one. This one is about a mixer here, mixer A. Okay, then another mixer we're supposed to use, mixer B here, and we can consider here a change in the phase shift, that is about a 90-degree phase shift. Okay, this one is about a 90-degree phase shift, and that 90-degree phase shift is to be applied to the another mixer. So mixer A has a signal that we consider that echo signal, mixer B, whichever the signal is there, that phase is to be shifted. Okay, so we can consider this one. This one is about your transmitter section, and we say that this one is about a transmitting signal from the transmitter, 90-degree phase shift from the transmitter. Again, we consider that this one is about a received signal here at this position. This one will be the received. This one is about your antenna now. Okay, receiving antenna. So we'll get that the signal to the mixer B, and this one is at the a mixer A both. Means we are getting a two channels. Okay, channel A and a channel B. This one is about A. We'll get the B here. And what will be the rotation? Okay, so that will be indicated by the a motor. Means that target is what will be the target direction. That target direction can be identified using the asynchronous motor, using the a motor. Okay, so we can consider that motor, and that what will be the signal at A here. We supposed to consider that a signal at A will be what? For example, we say that if the transmitted signal will be supposed to be a ET here, and that will be what a E0 cos of omega 0 t. That is about a transmitted. And then echo signal is to be what? Echo signal will be what? At a receiver one. So that will be what? A K. K is nothing but a constant frequency through the radar equation there. And E0 with respect to cos of omega 0 plus or minus omega d here. Okay, this will be plus or minus omega d. That is with respect to time plus what will be the phase change. Okay, so this one we'll say here was. Okay, so now we can find out here. Okay, omega 0 plus or minus omega d, what will be the shift with uh, change? Okay, Doppler frequency shift here plus pi, and that phi is nothing but what? At the initial detection level. Okay, at what will be the initial detection? But EA at this channel, we supposed to get EA here at the mixer is equal to what? What will be the constant here? Then E0 cos of plus or minus omega dt plus pi. That is about EA. And EB is nothing but what? Another constant here K. We say that K2, we say that K3. E0 cos of plus or minus, this one is about omega dt plus pi plus because we supposed to consider the pi by 2 here. Then if that target is approaching, okay, in that case there will be a positive value. Yeah, omega d will be a positive. Okay. So in that case, EA and EB both will be the a positive. This one, EA and EB will be positive. If the target is receding, this there will be a plus of minus omega d. Okay, so in that case, here both the way here, we supposed to consider that the omega d will be a minus here. So in that case, the sign here we supposed to consider in between that omega d and plus here. For a positive, this will be a plus all. For the receding, so this will be the minus. This will be minus and this will be a minus. So that from this we can find out the direction of the target motion. Target motion toward the radar or away from the radar. Okay, and that indicates or what will be the target direction that will be indicated through the motor. Okay, means we can say that through this equation we say that so channel A and channel B. Okay, so output waveform if we compare here, so then output of that channel B here that will be a lead or a lag. So plus pi by 2 or a minus pi by 2. Okay, so that's why we can say that plus pi by 2 or a minus pi by 2. Means we can say that leads or a lag that will be the output of the channel. And that lead or lag here, or we can say that there will be a change in the phase here. So we're supposed to use a motor, and that motor is called as a two-phase motor, and that motor will be rotating. And the direction of the motor rotation, that will be the indication of the direction of the target is in motion. Okay. So I say earlier, whatever the target we have, target will be proceeding toward the radar there. Okay. You can say that approaching to the radar, or a target will be receding, that is away from the radar. So according to that, what will be the phase change occur here? That phase change will indicate the direction of the a target motion. Okay, that will be indicate the direction of the target. So that's all about what we can say that a CW radar here, and we can use this ACW radar there to identify the velocity of the moving target or applications here for the CW radar here. We can consider that for the measurement of a relative velocity of the moving target. Okay, the use of this one what? Measurement of relative velocity. Measurement of a relative velocity of target. Measurement of a relative velocity of a target. That is about the applications of this particular. Or we can use the measurement of this relative velocity in the speed monitoring there. If in a vehicles we can use to identify that what is the approaching vehicle, which is nearer to okay approaching vehicle, what is the speed of that approaching vehicle there. Just like the police are using monitor the speed of the vehicles there. Okay, police department they are using the radar there, CW radar to measure the speed. That is the what speed gun there. Or we can use that what is the speed of the aircraft at the takeoff. Okay, so that is to be identified there. Or at a airport there, we can use to monitor the traffic here. We can say that airport traffic, control of a traffic light using the radar there, or we can use this regulation of a toll booth there. You know that in a toll plaza there is some line indicating, and if that vehicles reach toward that particular line, okay, the number of vehicles will be large at that particular line when that vehicles reach, so automatically that vehicle is to be, okay, no toll is to be paid by those vehicles. Okay, so this way to identify that what will be the regulation of the tolls and all toll booths there, regulation of your vehicles at the toll booth there, then vehicle counting, or we can use this for the measurement of speed and all. So there are the various applications of this CW radar there to measure the what will be the speed there, okay, for the vehicle, as well as we can use in a railway also using the speedometer, so anti-braking system that can be used there according to the speed and all, or changing the or identifying the what is the velocity of the a vehicle. Okay, so this way we can use a, a radar there, the various applications of the radar. Now we will proceed a discussion here with another type of radar that is called as a frequency modulated radar. So another topic that is about a frequency modulated radar. Okay, so we can say that a FM radar, FM frequency modulated CW radar. Okay, frequency modulated CW radar. So why this frequency modulated CW radars are used? So we have seen earlier there is a CW radar. So if you consider that band of that CW radar is to be a narrow one as compared to the what will be the a transmitted waveform, because we consider there earlier ft plus or minus ft. What will be the bandwidth of operation for the transmitted waveform and a bandwidth for the received wave. Okay, so if you compare here, so in that case that CW radar is major, or it will use to for the narrow band of operation. Okay, so means we can say that we consider earlier that is about a signal is to be transmitting. At what time signal is to be transmitted? At another time, what will be transmitted? So, as compared to the transmitting time, okay, signal is to be transmitted, and at what will be the time taken by the receiver to receive that a signal, echo signal. So, in that case, so we must apply the timing mark for the transmitted signal so that echo signal will be received properly there. So in that case, at what time your signal is to be transmitted and at what time there will be a return echo, and that return echo is to be identified there. So means to measure the accurate echo signal, so in that case we are supposed to consider that what will be the a transit time there. Transit time means what? Start of the time and end of the or echo signal time. Okay, so means we can say that signal is transmitting time at that particular time. So that pulse or that indication of the transmitting signal is to be there at the receiver. So means there will be a marking of the transmitted time or a transmitted signal, and there will be a marking for the receiver signal or echo signal. Therefore, for marking the transmitted signal or echo signal, so there may be a requirement for the finite spectrum there. So we could not use that is CW radar for the wideband of operation. So to increase the wideband operation of the CW radar, or we can say that our CW radar is used for the wideband of your applications or for a wideband of your operation there. So in that case, we supposed to use a modulation technique. In a modulation, either we can use a amplitude modulation or a frequency modulation or a phase modulation. So in that case, if supposed to be we are using the amplitude modulation, so then in that case, that amplitude modulation can be applied to the pulse there, and then pulse is to be a narrow there. And when we say that we supposed to use a pulse radar, then that pulse is to be narrow, so we can measure the spectrum accurately there. And that measurement of the spectrum occur in the what will be the broader transmitter spectrum. So in that case, we can use a broad spectrum, or we can use a wideband operation of this radar there. But again, if we consider that to improve again more for a wideband of operation, so we can use or we can widen the what will be the a transmitted signal there. So, so here, if we consider that a pulse, when we transmitting the pulse, then in that case the pulse is of a narrow band, narrow operation. Okay, so narrow band, or we can say that a narrow pulse will be there for the amplitude modulation. But in the case of a frequency modulated, so your carrier or your transmitted signal will be of a frequency modulated. If the carrier is of a frequency modulated, so naturally we will get a wide band of a operation. So we can consider here a frequency modulated CW radar for improvement in the wide band of your operation. Because at a transmitting signal, whatever the transmitting signal frequency is there, because of that signal is about a frequency modulated. So in that case, a transmitted frequency, there will be a deviation in the frequency of a transmitted signal. And that deviation in the frequency of a transmitted signal because of that frequency modulation. So at a receiver, okay, at a receiver, we're supposed to receive the echo signal, and that echo signal is a proportional to the what will be the carrier here. Okay, what will be the carrier we are. So if there will be the la- large deviation in the transmitted signal there, then at a receiver we supposed to get the echo signal, and that echo signal we are receiving at the receiver, that will be more accurate. So it will improve the wideband operation as well as it will improve the spectrum of a transmitted signal and it will improve the a signal to noise ratio at the receiver there. So that's why a frequency modulated radar that is to be used at a transmitting site means transmitted frequency it changes, and the transmitted frequency will be changes with a function of a time in a frequency modulated radar there. Means what we can say that we can say here for a given particular time, this one is about a time here, and this one is about your frequency. So we can say that your frequency will be changes with respect to a time. Okay, this is about a time. So there will be the variation in the a frequency there. Means transmitter frequency is changed with respect to the a time there. Okay. And then we are expecting the echo signal. We are receiving the echo signal. Again, that echo signal we are getting, there will be small deviation there. So this one is about a echo signal. This is about your transmitting signal, and this one will be the echo signal. And through that, we will measure the what will be the a range there. So range can be measured. T is equal to twice R by this C. T is equal to twice R by. This one is about a transmitted signal. This will be the echo signal. With this, we stop here. Thank you all of you. Continue next lecture. Thank you all.